welcome to OpenCV weekly webinar. And today we are going to talk about YOLO. And originally, I had thought that we are going to talk about YOLO v5, how to train a Snowman detector using YOLO v5. And that's still the plan. But I thought, while building the slides, I thought that it would be a good idea to start with YOLO, the original YOLO version 1, how version 2 builds on it, version 3, and then version 5. So we have the notebooks for training this, but I also have these elaborate slides on V1, V2, etc. So I decided that, okay, it would be a good idea to actually split it into 2 parts. So today we are going to do part 1. We have the notebooks for YOLO v5 training, which you can use to train the Snowman detector. But we will gradually build, and in part 2, we will go over YOLO v3, v5, and we will go over the training notebook also. So please bear with me. I hope that this is still very useful to you, because while creating these slides, I felt that we would not be doing justice to the Snowman detector if we did not understand the history of the YOLO family of detectors. So let's see how this goes. And I'm pretty certain that you will find it insightful. You'll especially for beginners who have not actually gone through the YOLO paper or papers, they will find a lot of value in what we present today. So
it promises to be the most intellectually rigorous Snowman detector you'll see all year, I bet.
Right. And we also have with us Phil Nelson, as always. He is the content manager at OpenCV.org. And Phil, welcome to the show. And thanks for putting this together.
Yeah. Happy New Year, y'all. Good to see everybody in the chat again. We're live on LinkedIn video again. If this is the first time joining us, there's a couple things we do here every single week. One of those is questions and answers from the live Zoom audience. If you're joining us via Zoom, you can click the little Q&A button at the bottom of your window and ask a question at any time, and we'll do our best to flow them into the conversation during the episode or save some time at the end to answer for dedicated question and answer time. We'll also be doing a special giveaway to one lucky winner. Satya, would you like to tell them what they'll win?
They will win a Deep Learning with PyTorch course. Because it is YOLO, some of the material actually has been taken directly from the course. So you'll get a sense of what kind of things we cover in the course as well.
Seeing a lot of people got those for the gifts over the holidays as well. A lot of people investing in their future.
That's good. In case you have already bought, you can buy a different course. And in case you have bought the entire package, you answered that question. We are coming up with deep learning with TensorFlow and Keras by the end of this month. The first tranche will be released, and you can get access to that. So we are flexible. If you win something, you will get something interesting.
Yeah, sounds good. And as we have to have one caveat, which is if you've won recently, say the last couple of months, please do not answer. Give other people a chance to get their
unless we are stuck and nobody's answering, you can answer.
It has happened a few times. We have finally stumped the audience a couple of times. It's a constant battle with these super smart guests we have in the chat.
All right, so let me share my screen. Okay, so YOLO stands for You Only Look Once. Obviously, it's a play on the original YOLO, You Only Live Once. And I like this
or if
family.
you're James Bond, you only live twice.
That's right. Let me make this full screen and see. Start slideshow. Can you still see it?
Yep, looks good.
Okay, great. So I'll start with a question to you, Phil. Now, in classical object detection, we used to do this, we would actually collect a lot of images of the object that we want to detect, and collect a lot of images of objects that were not that object, right? So for example, face detector, we would collect a lot of pictures of faces, and then we will collect a lot of pictures which were not faces, and then we would build a classifier and then run this classifier on multiple locations on the image, and that was a detector. Now, there's a flaw in this kind of thinking. Now, let me ask you, Phil, in a face, right? What makes a face when you see this image? In just, you can describe in words, what makes this a face?
Yeah, I would expect, eyes, eyebrows, nose, mouth, just the classical points.
So some features of the face, right, make it a face. That's fine. That's one way of thinking. But let's say we have a mask here, right? You can still say very confidently that this is a face. So Phil can actually modify his statement and say that, oh, we only need to see a collection of features, right?
A
But these are all
subset of the features.
yeah, a subset of the features. That's right. But that's not actually true. That's not actually true. Suppose you had all the information in this picture, except for the information in the green box where all the facial features were there, right? So you could look at this image, but you don't have information of the facial features, but you can still, with a very high degree of confidence, say that there is a face inside the green box, in that green box.
It would be very surprising if there weren't a face behind that green box. Yes.
Right. It would be a contrived example.
To my human brain, I would be very surprised.
Right. It would be a contrived example, like here you blocked it, right? So the thing is that even if you did not see the face, you are able to predict that there is a face based on the context of the image. And this was a big flaw in classical object detectors, where we left out the context, right? We were training only on objects, and we were saying that the features of the objects were the only things important for detecting the object.
Which has another flaw too, in that human beings come in all shapes and sizes with, not everybody has two eyes or any eyes, or the same kind of nose you might expect, or so forth.
Yeah, so context is important, and that's what these new methods, deep learning based methods, help us do. That brings us to YOLO, which looks at the entire image to do the prediction. So that was, when I was first reading the YOLO paper, I think it was back in 2016 or so, that was the first thing that struck me, that, okay, this is something very obvious, that these new detectors are taking the whole image into consideration while making a prediction, which is how we humans also do it, right? Let's say you look at a person and some parts of them are occluded, you can still make out that, okay, the hand is there, the face must be somewhere around this.
We can make a really good educated guess that there's probably a person there. Yeah.
Right. So now YOLO architecture, the first YOLO architecture was something like this, right? You have an input image, you resize it to 448 by 448 by 3, and then you have some convolutional layers, and then you have some fully connected layers, and then you do non-maximum suppression on top of it. Now, if you don't understand these terms, it doesn't matter. What the more important thing is that you see this blue box, which we call convolutional layers. It is a feature extractor. It is basically a collection of layers that identify different features of the face, or different features of the context, right, of the things that surround the face, which can indicate where the face is. So in these convolutional layers, we could be learning, in some of the layers, you could actually see eyes and nose, etc., being shown. But if you have actually gone through image classification, you will see that this network looks very similar to image classification networks, right? Because the idea is very similar. What we are trying to do is we are trying to find the features in the face or around the face, which will be used to detect. So classification and object detection, they are very tightly intertwined, right? So let's look inside. I mean, for this discussion, let's actually not even worry about how these features are extracted. Just imagine that there are some filters that are applied to different parts of the image. And this is what the convolutional layers are doing. They are extracting features. And then we have some fully connected layers, which allow us to do object detection. And we'll come to it in a little bit. So as we all know that, ImageNet, which is a very big data set of images, people use that a lot for fine tuning. Whenever they build something for image classification, you start with ImageNet. ImageNet fine tuning is also used for object detection. So once you have this image, which is, ImageNet images are 224 by 224. So for using it in object detection in YOLO, for example, they have to actually modify it to 448 by 448. But they first do the fine tuning of the network on ImageNet at the original 224 resolution. Then they simply use the same network. They change the size of the image to 448, but can continue using the same network. The weights that were learned in the 224 model, right, to do the detection on this YOLO.
That photo of the dog and the bicycle and the car, I feel like I've seen it 1,000 times now.
So this
it's like one of the most famous photos in computer vision and AI now, probably.
Yeah, so this was in the original YOLO paper, and also the slides. These original slides also, they are very good slides to look at. We will share them. If you go, I think YOLO has, the YOLO website, Joseph Redmond's website has links to these slides. If you search for YOLO CVPR 2016 and YOLO 9000 slides, you should be able to find out. And if you don't, I will share it, in our YouTube link after this webinar.
I'll track those down for the audience.
Yeah, Phil, actually, you can also Google search them and find those slides. So the point I'm trying to make here is that YOLO is also fine-tuned on ImageNet, but the resolutions of the images are different. And this is how, you start fine-tuning using 224 resolution, but you upgrade the model to 448. You keep the same weights. And we'll learn later on in YOLO v2 that that was not a very good idea, right? So the important thing to note here is that when we go from version 1 to version 2, etc., there are some things that only through experimentation. And this was one classic example that they could get a huge jump in accuracy once they modified this scheme a little bit. So we'll come to it again, how they changed the fine tuning when they moved from version 1 to version 2. Okay, so how does this YOLO version 1 work? They basically divide the image into grids. So here you can see that the image has been divided into 7 by 7 grids. And if you remember, the original size of the image was 448 by 448. And that whole image has been divided into these grids, or they call it cells. Now, for each cell predicts 2 bounding boxes. And it also predicts the confidence for each bounding box. Okay, and we'll see an example. For example, if you look at these, there are 2 bounding boxes that this cell is responsible for predicting. And if you look at the width of the bounding box, that is showing the confidence, right? So each cell will produce 2 bounding boxes and only 2 bounding boxes, which means that, can somebody guess? This is not the question that will actually fetch you the free course, but can somebody guess what is the maximum number of objects that YOLO v1 can detect, knowing what I have just told?
If you answer correctly, you'll win the first winner of the OpenCV No Prize.
No, but I want to see,
Shout out to the Marble Bullpen for that one.
Okay, so what's the answer? Did somebody answer?
Yeah, I don't know what the answer is.
The answer is 98.
Okay, yeah, Zach in the chat here got it, as well as somebody whose name is way too cool for me to try to pronounce.
Right. So a maximum of, that that too, you'll have to adjust some thresholds, etc. But maximum you can predict 98 objects.
Do you maybe I can predict people are going to ask why? Why is the limit 98?
Okay, so there are, like I said, that there are 7 by 7 cells. This is by design, right? So there are 49 cells, and each cell can have a maximum of 2 bounding boxes, right? And let's say each bounding box is showing things with very high confidence, right? Then we can just say that there are two times 49. But in practice, there will be overlapping bounding boxes. So you would do non-maximum suppression, etc. In practice, it would be much less than 98, but I'm just saying the theoretical maximum would be 98. Does that make sense?
Yeah, totally.
Okay. So now, what about empty cells, right? Empty cells will still predict 2 bounding boxes, but the confidence would be low. And in the last stage of the detector, we will remove all the boxes which have low confidence, right? So that is how we will get rid of all these different boxes. Now, you can see that what I just said, that the total
number looks like the first time I tried to train a model.
Right. I mean, if you don't set your thresholds, you will see that you will see all these boxes everywhere, right? So the total number of predicted bounding boxes is 98. Okay. Now, each cell also produces a class or the probability of a class. So if you actually, what it's predicting is that suppose there was an object in this box, in this area, what is the probability that it belongs to a certain class, right? So it's not saying whether or not there is an object here, but suppose there was an object, then what would be the probability, right, that it is a certain class? For example, this whole image has been divided into these various classes. We are looking at only the top class that this cell predicts. So you can see that all these different cells on the top right-hand side, they predict that this is a car. And all the all the ones at the bottom, they predict that it's a dining table, right? We know that it's not a dining table, but that's what the class prediction would be, because it doesn't have the concept of ground. There is no ground class in ImageNet. There's a dining table class, and that's what it thinks. But fortunately, there will be no bounding boxes associated with those. The confidence of the bounding boxes would be too low. And so we will never detect a dining table in this. But if you look at only the classes that a cell produces, you will see a map like this. And this is all, I have copied many of these images from the original slides, even though I missed the reference in a few places. Many of these are from the original slides. Some of them are from the paper.
I dropped that PDF link in the chat as well for folks.
That's great. Right. There's a Google Docs slides also.
See if I can track that down as well.
Okay. So now those 98 classes, right? And I'm showing just a few of those. If you actually color code them, so you have the bounding boxes and the probabilities. The probability of the bounding box is given by the thickness, right? And the class, the color actually represents the class. You combine all those things together, and you can start seeing a picture that emerges like this. Now, there are too many boxes, obviously. What you need to do is threshold the confidence and do something called non-maximum suppression. If there are 2 overlapping bounding boxes, you only pick the dominant bounding box, right? And once you do that, non-maximum suppression plus thresholding, you get these 3 bounding boxes remain, and the others are, either the thresholds are too low or they are overlapping with something else. Is everything clear until this point?
It's clear to me. I mean, I have a little bit of context starting out, but
yeah.
Looks like the chat is saying yes so far. Thanks,
okay.
Chetan. Okay.
So now, let's look at the architecture, right? Forget about the rest of the things. Let's look at the input and the output only. And sometimes it's very good to think about, forget about what's in the middle, think about it as a black box and look at the input and what is the output. So when you look at YOLO V1 output, we will see that this is a tensor, right? And let's look at what does this tensor say. This is a tensor of size 7 by 7, and you can imagine what the 7 by 7 is. The 7 by 7 corresponds to the cells that we had created initially. And as I had said, that for every cell, there are 2 bounding boxes. And when I say a bounding box is basically a collection of 4 coordinates, right? X, Y, width, and height, or you could have other representations also. No matter what representation you use, a bounding box, which is axis aligned, will have 4 coordinates, right? So for 4 coordinates and then 1 confidence per bounding box. And suppose there are 2 bounding boxes, then we have 10 of those numbers, right? And there are n classes for Pascal, for example, a VOC, there are 20 classes. So there are a total of 20, the depth. So the width and height are 7 by 7. And along the depth, we have these additional dimensions. The first 10 dimensions are for, the 4 coordinates plus confidence, the 4 coordinates plus confidence. And the last 20 represent the class probabilities, right? So the total dimension is basically 1470. Is that clear?
It's about as clear as it could be to me, but I'm my brain hates numbers, so let's open it up to the chat. Any questions here? I see actually one from Sam McGraw would like to know how, when the boxes sort of overlap, like how do you separate the items from each other, or does it just not care about that?
Yeah, so this is called non-maximum suppression. So you pick the bounding, let's say there are 2 overlapping bounding boxes, right? And one of them is predicting a dog. The other also is predicting a dog because, it can look at only the face of the dog and say that it's a dog. But these bounding boxes are overlapping, right? So you could pick the one that has a higher confidence, right? And you can leave out the other one, right? And so this, the Google search term you should look for is non-maximum suppression.
Non-maximum suppression.
Yeah, NMS. And in practice, it's very easy to implement. You can also get there are some tools for non-maximum suppression off the shelf that you can use as well.
All right,
but the important thing here to note here is that we started with an image and we ended with a tensor, and each cell in this tensor, and tensor is basically a multidimensional matrix. You can think about a tensor as a 3D matrix, nothing more fancy. Each cell is predicting bounding boxes, and the output is being predicted by the entire image, right? Not through a small portion of the image, but the entire image is being used to predict the classes and the bounding boxes for all the classes, right? It's not looking at the portion of the image only, right? It is using the entire image. Ultimately, through the features, it could be using only a portion of the image, but it's not making a premature optimization by looking at only portions of the image. Does that make sense? So this is going back to my initial thought about, we should not be looking at only the portion of the image. We should be looking at the entire image for the context, which will allow us to do better predictions.
Yeah, makes sense.
So now the question is, how do you train the data, right? How do you train this network? During training, in any neural network, usually when you have supervised learning, when you're trying to use a neural network for a supervised learning task, you train the network, you give the network the same information that you want it to predict. So in this case, you will give it many images and bounding boxes around the images and the class label. So here, for example, the bounding boxes are obviously the coordinates, but we also have the class label, which is a dog here, right? And the bicycle and the car. So this information on thousands of images, tens of thousands of images, sometimes even millions of images, is fed to the neural network, and it is asked to predict the same thing. So the input during training is the same as the output that you want at the time of inference when you have trained the model. So now, because YOLO has this grid structure and everything, so how do you actually do it, right? So now from the ground truth, when we are training, we know that there is a car here because that's the purpose of training. We have been supplied with bounding boxes, the class label, and where this car is. So the center of the image, that is the cell responsible for predicting this car, right? So now we found, okay, this cell at the center is responsible for predicting the car. And then we basically increase the, as I had said before, there are two bounding boxes that this cell is going to predict, right? So we find the bounding box which is closest in dimension to the original, and we increase its confidence during training, and we decrease the confidence of the other bounding box, right? So that way we have the center, the cell is predicting that there is a car here, and it's also predicting the correct bounding box. It's lowering the threshold or lowering the confidence of the other bounding box, right? So this is what I just mentioned, visually shown. The confidence, as I said, has been represented using the thickness. And you decrease the confidence of the second box. Okay. Now, what happens when there is no class, right? So it doesn't matter what class it is predicting, all we need to do is reduce the confidence of the bounding boxes. And that's what YOLO V1 did for cells which were not responsible for predicting anything. In this case, the floor is not one of the classes that we are looking at. So it's not going to predict anything. Now, this is, again, the final network. And if you, actually, I'm going to skip over some of these things. If you look at the actual architecture, right, this is straight up from the paper. This is what it looks like, the internal architecture, the convolutional layers, etc. And the exact architecture is actually not very important, right, for understanding the network. It is important when you want to optimize the network and when you want to make sure that the GPU utilization is good, etc. But from a understanding point of view, all we need to know is that these convolutional layers are extracting features which are important for detecting the object, right? And if we select the layers in certain ways, the performance can change. The performance would be better. But from a theoretical point of view, just from the understanding the network point of view, we don't need to know what is the exact structure, or we don't have to worry what is the exact structure inside these layers. So when you're reading this paper, right, I like, especially for beginners, I always tell people that almost have this learning layer by layer, right? You first understand, without understanding everything, you first understand what is the input, what is the output, and think about the layers in between as a black box, right? Don't worry too much about it. Otherwise, you'll just get caught up in the detail. And then once you have understood, okay, this is what is being predicted, then try to dig in and figure out, oh, why these choices were made, or why such and such choices were made. Try to also read up on what were the alternative choices, right? Why did they not make some other choice? And a lot of times it happens, especially with this feature extracted portion, that there could be multiple good choices. It's not that the authors made the best choice. And that is why you see that, they do experimentation and they figure out that, by doing such and such, you can improve the performance of the architecture. And many times there is no good way to tell beforehand that, oh, this is the best architecture. You have to do experimentation with your data to figure out what is the best architecture, etc.
Yes, clearly not a solved problem for sure.
Yeah. Yeah. So the other thing that the network needs while training is the loss function, right? The loss function is basically a way of telling the network that it made a mistake. The loss is high when the network is making a mistake, but the choice of the loss function also matters, right? Because it could be making mistakes in many different ways. One could be what we call the localization error, right? Localization means, let's say it has detected, it is saying that it is a dog, there's a dog in the picture, but the bounding box corresponding to the dog is off. You have to account for that. The bounding box needs to be right on the dog. It's not sufficient that, okay, it has detected that there's a dog, but the bounding box also needs to be correctly placed, right? So you can see that there is an error term which corresponds to localization. It says that the X and Y coordinates should be right. And then the width and height also need to be right, right? So there is the loss function encodes these two things. Now you may be wondering, oh, why is this funny thing? Why are we taking the square root of the width and the square root of the height and then squaring them? Why not width and height? And these are the kinds of things that you get through experimentation. In the paper, they will explain, why these choices were made. But I want people to understand that these kinds of, when people make these kinds of choices, it's not very obvious. They didn't just come up with this saying that, oh, it is obvious that you have to take the square root of width and the square root of height. They did some experiments and figured out that this tends to work best. And then they can come up with some explanation why this tends to work best. So a lot of times, I emphasize that you have to experiment when you're building a neural network, when you're training a neural network. You have to experiment with the loss function. You have to experiment with many different things to come up with the right one. Nobody knows out of the box, right? There is no obvious way. And the good thing about the YOLO 9000 paper, YOLO V2 paper, is that they also mention what did not work. I really like that paper because they also mention that what did not work. There were some ideas that you would think that, oh, this is a good idea, it should work, and it doesn't, right? And nobody knows exactly why it doesn't work. We just know that when you try it, it produces inferior results, even though intuitively it makes sense that it would produce better results. So experiment. That is how you know the truth.
And knowing where these things fail is, if anything, possibly more important than knowing where they succeed.
Yeah, I agree. Right. So similarly, you also have the confidence associated with the bounding box. The thickness of the bounding box that I was saying, that also needs to be high. Otherwise, it's no use. So there is, in the loss function, we also have a term that encodes that loss. And finally, we also need to make sure that, if there is no object, the confidence of the bounding boxes in that region is small. And finally, the object probability, that which object is there if the bounding box is present, right? So you can see this complicated loss function, but if you break it down, go one by one, you will see that it's not very difficult, right? It's pretty easy to understand what's going on. What are they trying to optimize? And once you minimize this error, you get an object detector, which is really good, right? So the choice of loss function, when you are actually not just training a neural network, when you're doing the research to come up with a new object detector, new classification network, etc., the choice of loss function can mean a lot, right? So, but let's say you're training a neural network that is already established, like let's say you're training YOLO v5, you don't worry about this because they have already figured out what would be a good loss function. But when you're architecting, you're building something from scratch, then the loss function, the choice of loss function is very, very important. And the final thing is that, to give more flexibility, they also sometimes have these weights associated with different terms, so that, how much weight do you give? And this is almost like a black art. You have to experiment and see that, okay, I'll give half weight to this and half weight to that, and maybe that's the right answer. So you'll have to experiment with some of these weights to figure out what is the right answer, what is the right loss function. So the pros of YOLO are that it was much faster than what was called faster RCNN. Faster RCNN before YOLO was the dominant object detector. It is still very dominant. It gives very high quality results. Maybe not so much these days. These days there are better networks out there. But for the longest time, even until 2017, 2018, faster RCNN was pretty dominant. It gave very high quality results, but it was very slow in spite of the name. It was just faster than fast RCNN, which was faster than RCNN, and so on. But the problem with YOLO is that it misses small objects, and this is YOLO version 1, and it also misses objects at multiple scales, right? If it cannot handle multi-scale objects. So, and that's pretty much because the scale of the feature map, output feature map, the 7x7 grid, that limits what it can do, right? So that brings us to the question, right? And I want a little bit long form question answer here, right? Now, you can see that I don't know how many.
So for this is for folks joining us in Zoom.
Yeah.
Satya is going to ask a question here. You will win your choice of OpenCV courses, I guess.
Yes.
Is that what we're pitching?
Yeah.
So yeah, follow his instructions here. And if you've won recently, please don't answer. If you won in the last couple of months, some of you are just too good at this. So thanks.
Right. Now, let's say you ran YOLO v1 on this image, and frankly, I have not run it on this image, but let's say you ran YOLO v1 on this image. Give me the reasoning, how many, these are clearly less than 98 images, right? Less than 98 cars. It's also less than 49 cars. Do you think, and these are easy, let's say you have the best training data, right? So detecting these, these should be very easy, you would think, right? Because clearly it's, the examples are easy. You got the best training set, you trained it on millions of images, everything, was perfect. Would you detect all the cars, right, in this image? And
answer in the form of
how many can you expect? You don't need to get the exact answer because I don't know the exact answer, but I want to hear the reasoning, whether you would be able to detect all the cars. Give me some number. How many would you think would be a reasonable number?
Yeah, I see a bunch of answers here. I'm not exactly sure what's correct. But
let me look at the chat.
Pop open the chat here. And they really want this one. There's some good answers here. They seem reasonable, but I'm not 100% certain.
Okay, at least I see one right answer.
Okay.
So
Which is?
I mean, if you think about YOLO, right? Even though we have a grid of 7x7, in a single row, you can only detect 7 of those, right? So there will be only 7 rows, 7 objects in a single row. So there are 2 rows here if you think about it. So approximately 14 is would be my guess, right? And it could be, I've not run YOLO V1 on this image, so I don't know for sure, but you can make sure that, no matter how well you train the network, no matter what your data is, no matter what you do, you will not get all the cars. That's the point I want to make. That
Yeah, I see it. A couple of people answered. I see Kevin said the YOLO boxes are larger than the cars, so you would probably miss about half of them. Was an interesting guess.
More than that, the important thing is that there are only 7 in a row that can be detected.
Right.
Right. And so no matter what you do, the architecture limits what you can do, right, with this. And this was and this is not a contrived example. Somebody, I heard this story that somebody was trying to detect YOLO, cars in a parking lot using YOLO V1, and they tried many different. They kept increasing the data set size, thinking that if they only had the right data set, this problem will be fixed. Yeah. So anybody who made this argument that only 7 in a row, I think the first one.
Yeah, I'll dig through the chats here. It's looking like it's like a couple people. I'll have to do it at post show.
Okay.
Too many good answers.
But the important thing is that we have to have that argument, right? In the not just the answer, but
not just the number. Yeah. Gotcha.
Okay. So, God, I've just covered YOLO V1. It's a.
This is going to be a not just a 2-parter. This is going to be maybe a multi-part episode.
I just want to ask people: is it interesting? Is it useful, or did I just waste a bunch of your time explaining something which is not even used these days? YOLO V1 is not used, obviously.
Seems like it's a hit based on the reactions in the chat here. Thanks, folks.
Okay. Thanks. Yeah, we need to have some historical context, but it also gives you the kinds of things to look for when you're using an architecture. What are the ideas people worked on, and what are the current set of ideas? You cannot understand what the impact of the current ideas if you do not know the history, what did not work, where it all started, etc. Right? So giving some context, as I said in the beginning, adds a lot to your understanding of the current architectures. Without that context, you'll lose out. So the next model in this family is called YOLO V2. That is the model. The paper was called YOLO 9000. So YOLO 9000 is the system that they used to train. The actual model is YOLO V2. So interchangeably, most of the people call it YOLO V2. But if you read the paper, it will be called YOLO 9000. And the word 9000 comes from the fact that it can detect 9,000 categories of objects.
That's funny. I actually thought it was just a reference to the Dragon Ball Z meme, like power level over 9,000 or whatever.
It could be,
I just see Vegeta in my mind when I see it.
Right. So now we had seen that in YOLO V1, this is the way fine-tuning was done, that they trained it on ImageNet and then just did not do anything. They used the weights and fine-tuned the object detector. They just resized the network, right? Resized the input image. No other change was made. Turns out that was not a very good idea. If you fine-tune, again, you train it on 224 by 224 ImageNet images, and then resize the images and fine-tune for a few epochs, like they used 10 epochs. And then, you can forget about the classification part and focus on object detection. This simple thing, this 2-step process actually gave them a 3.5, as far as I can remember, 3.5% increase in accuracy. And accuracy is measured in mean average precision. So that number increased by 3.5%, which is a huge jump. So what was happening is that earlier, it was when they jumped from this 224 to 448 object detector in one shot, the fine-tuning mechanism was burdened with learning too much, right? It had to learn the increase in scale, and it also had to learn the object detection, objectness, and things like that, right? So it was too much for it to learn in one shot. But if you help it in two shots, right? In the first phase, it is only learning about the increase in scale. So you increase the scale of the image and then fine-tuned it, it actually produces better results. And then in the second phase, you are trying to train the object detector. So this little mechanism actually got them 3.5% increase in accuracy. Again, why didn't they do it in the first shot? It's not, I mean, it's not obvious, right? You have to try these different things, and then you see that, oh, these are the things that work, and some other things that don't work. The second thing that they did was called anchor boxes. If you remember that there were two bounding boxes that were being predicted in YOLO V1 per cell. But those bounding boxes, we did not help those bounding boxes. We did not say what should be the aspect ratio of those boxes, what should be, where should it start from, right? So the initialization was sort of random. But in YOLO V2, they came up with this concept of anchor boxes. And this was not something original for them. This concept has been around for some time. You know, a lot of object detectors use anchor boxes. What they say is that don't start with random initialization, start with some predefined anchor boxes. For example, there are 9 boxes that you see here, and I have just clubbed them into groups of 3 so that it's easier to see. For example, if you're doing, if you're training a pedestrian detector, then you would want to use anchor boxes which are vertical, right? Instead of cars, which you may want to do anchor boxes which are horizontal. For some other objects, you may want anchor boxes which are squares, right? And if you start with this initialization, you're helping the network. Yeah, it's not starting from 0. It is just learning the delta between. You start with these anchor boxes, and then you learn the delta. How should these anchor boxes be fixed so that it best fits the object? So when you're focusing on the delta, you can think about it as that all your energy is being spent on finding this, finding one of these boxes first, which is a coarse grained. You at a high level, one of these boxes best fits the object. And then you're doing a fine-grained optimization on top of it so that it fits the best. And most of your effort is being spent in doing this better fitting of the data. So that's why these anchor boxes are very popular. They work really well. But the second thing they determined was that what boxes should they choose? What aspect ratios should they choose, right? You could start with, this one is 2:1, this is 1:2, and then this is 1:1. What kind of boxes would be a good choice? And the simple answer is that let the data tell you, right? Why do you even want to do that yourself? So for example, if you're trying to detect cars, then you would want horizontal bounding boxes, but you should not be telling it, right? You have the training data. The training data already has information about what kind of bounding boxes are there. So you could take all the bounding boxes in the training set and do a clustering on it. K-means is a standard way of clustering data. And when you do this clustering, you can, in K-means, the K is a parameter. It's a hyperparameter. You choose what K is, which means that how many clusters do you want for your bounding boxes, right? And when they set it to 5, you can see that it's starting to get better, right? You can even use more clusters, but if you use a lot of bounding boxes, then you're spending a lot of time evaluating them as well, right? The size of the tensor goes up. And they found that
necessarily have performance implications.
Yeah, it will have performance implications. Even though the accuracy is going up, it's not free, right? It is coming at the cost of performance. So they picked 5, and these are the kinds of bounding boxes that you get from the cluster. One of them is a square, 3 of them are, vertical, and one of them is horizontal. And I believe this was in the Pascal VOC dataset. But your dataset, when you try to train YOLO V2 on your dataset, it could be different. You could be training, I don't know, flowers, right? And flowers may be squares. Most of the flowers are circular or something like that. And maybe that would be the best option for you. But the good news is that you don't have to worry about it. YOLO V2 and YOLO V3, all versions of YOLO will automatically do this clustering for you, and you don't have to worry about, what is the right aspect ratio for the anchor boxes. So, okay, now what? The other thing they did was fine-grained features. First of all, they used a 13 by 13 map. And we remember that YOLO V1 was using 7 by 7 feature map in the end. So 13 by 13 is already creating, more fine-grained features. But they also have, in the network, they also have another path where they don't go all the way down to 13 by 13. They go at 26 by 26 feature map also. And that produces even more fine-grained optimization. And then they combine the two information to produce the final bounding boxes. So they do this fine-grained feature extraction as well. Another interesting thing was multi-scale training. So because this network is fully convolutional, you can actually change the input size of input image size. And the input image size, they train on multiple scales, 320 in multiples of 32. So 320 by 320 was the smallest image size. And then you upgrade it to 352 by 352, and then all the way to 608 by 608. I cannot remember the exact details, but maybe they randomly chose images that some of the images were 320 by 320, other images were 352 by 352, etc. So now you can see that this network is being trained on multiple scales. And interesting things happen. You may think that, oh, what's the point? You can see the bicycle at the right resolution, but things start changing at multiple resolutions. Some of the features vanish at lower resolution. That's an obvious one. But sometimes at lower resolution, you may also start seeing these fake features. Some features appear at lower resolution that were not there in higher resolution, just because of a combination of how the downscaling is done. So funny things happen when you look at things at different scales. So YOLO V2 had this multi-scale training, which was very, very interesting. I think this multi-scale training gave them another 1.5% or some boost in accuracy. I cannot remember the exact number. It's in the slides that were shared, that they have shared. The second thing they did was they used a better architecture. The convolutional layers that they used something called Darknet 19. It had fewer parameters than the original YOLO V1, and it also had higher GPU utilization. This is something that came as a surprise to me when I was reading the paper back in the day. I don't remember 2017 or so. That just because something has fewer, just because an architecture is using fewer number of operations, let's say 2 architectures, A and B, are using the same number of gigaflops, doesn't mean that the frame rate would be the same. It is possible that some architecture, which is 2 architectures which are both using 10 gigaflops, one of them is running at 200 frames a second and the other one is running at 100 frames a second. And that's based on how much of the GPU is being utilized, right? So to make the calculation possible, things need to be moved to the GPU, they need to be executed properly. But a lot of, even if it is the same number of operations, if it takes a long time to transfer things to the GPU, or there are some operations which are taking more time, even though they are not consuming computational power, it's making the GPU wait. It can have an impact on the performance. So that was something interesting. YOLO v2 was also jointly trained for classification and detection. So they had two different loss functions. One was for detection. As we saw the loss function for detection, it would take into account, the location of the object, etc. But they also used data sets where they did not have bounding box information. And when they were using those images during the training process, they would use a different loss function, right? So they would use a classification loss function and still updates the same weights. Now, you may think that why does it even work? It works because no matter whether you're detecting an object or classifying an object, the same kinds of features are useful. So you can use the same network, the same backbone for detecting the features, right? For extracting the features. So, even though you don't have bounding box information for a lot of images, you can use that information to detect, to actually train the network. It gets better. And surprisingly, after you do this kind of training, you will find that it will detect the bounding boxes for even classes that it was not trained on. Let's say you had a new class, helicopter. Let's say there was a new class called helicopter where you did not have bounding box information for the helicopter. You had images of helicopters. You knew that this image contains helicopters, but you did not have bounding box information. But YOLO v2 could detect the location of helicopters, even though it had never, in the training set, there were no helicopters where the bounding boxes were present. Pretty interesting idea, right? That you're able to do such things. And that's why it was called YOLO, the system, they called it YOLO 9000. It could detect location of 9,000 different categories. So very good ideas. I highly recommend that paper. It gives you a sense of, how to get the accuracy to a level, you push on multiple fronts. It's not like one idea is going to get you there. You keep pushing on different little things, and finally you get the right answer.
It's true of many things in life, Satya. It's just good general advice.
Right. So yeah, that's pretty much what I wanted to cover in this session. People who want to go and dive into the YOLO 5 Snowman Detector, I don't want to disappoint them. Phil is going to share the links to the notebooks that we will cover in part 2. And in part 2, I will also cover YOLO v3 and YOLO v5. So before we go there, there's a lot of controversy about YOLO v5, whether, because YOLO v5 is, it's not from the same branch. It's not even the same GitHub repository. So a lot of people say that the company Ultralytics, which published YOLO v5, they just use the YOLO name to come up with this architecture, right? YOLO v5 is broadly based on YOLO v3, the PyTorch implementation of YOLO v3. And so, but we still chose YOLO v5 for this demo. Part of the reason is that, we should not, we often think about scientific contribution as who gets the credit for what, right? That's a narrow view of thinking about scientific contribution. The important thing we have to note here is the company Ultralytics, no matter what they called it, they still published this architecture. They published the code, everything free of charge for anybody to use. And that is a solid contribution, right? They are improving this with the help of the community. It's open source. Everybody gets to use it. Okay, you could argue that, they did a little bit of cheap trick to get the YOLO v5 name when YOLO v4 was just published 1 month before by a different group. It is a little bit of a cheap trick, but in the grand scheme of things, who cares? they still published a good code base that we can all use free of charge, right? So we should be more forgiving to people who contribute, right? So a lot of people who are actually outraged by how could you use YOLO v5, right? People who actually contributed code, let's say the author of YOLO v4, they have the right to be outraged by YOLO v5 name. But if you have not contributed anything to the open source community and you're outraged, who cares, right? Those people don't have the right to be outraged by somebody who is actually contributing, even though they used I don't fully approve that you should use the name YOLO v5, but it doesn't bother me that much, right? It doesn't bother me at all, actually. Let them have their fun, but the more important thing is that they contributed solid code to the community, and that's the more important thing, right? So at least that's my take on this, and we will go over both YOLO v3 and YOLO v5 in part 2 of this presentation. Unfortunately, I don't think we can do part 2 next week. It will have to wait a few weeks because we have people scheduled for the next few weeks.
Yeah, I'll see what I can do with some schedule juggling here to try to give a good a good date for episode 2.
Okay. Yeah. So I mean, when I started creating these slides, I was thinking that I was just going to create YOLO v5, but it just was not. It didn't feel right because I was not able to explain things without having the context of all these previous YOLO models. So I feel, I hope that this was still a useful talk. And in part 2, we will cover what we actually promised.
I definitely learned a lot. It seems like the folks in the chat did as well. Thanks for joining us again, folks. We will be back next week. I believe our guest is scheduled to be Kat Scott from Ross. That'll be fun. Always a pleasure to have her on the show. Yeah, you want to do a quick question? Take one quick question and then close us out. Maybe does that sound good?
What's
I've got one here. So maybe a little bit self-promo-y, but one anonymous attendee asks, is there a program or course where I can learn all these concepts, perhaps OpenCV courses?
Yes, OpenCV has a collection of courses. We have Computer Vision 1, which is an introductory course in computer vision. We also Computer Vision 2, which is a course focused on applications. And the third one is Deep Learning with PyTorch. So these 3 courses are, they will take you from, like I like to say, from basics to mastery. There's also one very basic course called OpenCV for beginners. It is full of applications, etc. But it doesn't go, it's a 1-month course. It doesn't go into depth of these applications. It's a fun course. It's a short, fun, and very affordable course, but it doesn't go into the depth like this one. So if you want to learn these concepts in deep learning with PyTorch is the course. If you are interested in the Keras and TensorFlow course, we will be releasing that soon as well. So that's coming sometime later this month. Will be the first few modules, and then we will keep releasing the modules in every 30 days.
Great. Yeah, I've seen a lot of traffic on LinkedIn of folks taking their first steps in computer vision and AI, and it's really gratifying to be a part of that just by being part of OpenCV.
It's great. And it supports the library also, that's the main thing, that we were able to get some revenue for OpenCV so that we could hire people to support the library. So that's...
Yeah, absolutely. Yeah, thanks again for joining us, folks. Satya, you want to take us home?
Yeah, thank you so much. Let me just stop sharing the screen.
Already did.
Oh, I already did. Great. Thank you so much, everybody, for joining us, and wish you a very happy New Year. If you're thinking whether New Year resolutions work or not, don't, you get this extra energy for free during New Year, no matter where it comes from, no matter how irrational it is, use that extra energy to do something good, to do whatever you dream of. Use New Year's resolution. Who cares, right? If it works for you, even though it works for a month or two, use it to your advantage and get something done. So all the best, everybody. Thank you, Phil. Thank you, everybody, for joining this. In our next part, we will cover what we promised, YOLO V5, YOLO V3 and YOLO V5, Snowman Detector. Thank you.
Take care, folks. We'll see you next Thursday, 9 a.m. sharp Pacific.
Thanks so much for watching this episode of the webinar. Please hit that like button, subscribe, and don't forget to tap the little bell icon to be notified when new episodes drop. This week's episode was brought to you by OpenCV Courses. Learn computer vision from the experts at opencv.org/courses. If you'd like to be in the audience next week, subscribe to the OpenCV newsletter.